Now we know the integrals of sine and cosine, but what about the other trig functions? It turns out that substitution is what allows us to figure this out. So these last examples will just be about the trig functions by themselves. Let's use substitution. To find an antiderivative, or all the antiderivatives, also known as the indefinite integral of tangent. Now, as written, this is not terribly clear to me how I would even proceed using substitution. What do I substitute? And what turns out to be useful is just, as often is the case with trig and hyperbolic functions, let's just rewrite everything in terms of sine and cosine. So I'll write this as sine of theta divided by cosine of theta d theta. And now I need to make a good substitution. Now, a good substitution, as we've seen, is something that we know the derivative of and is making the problem more complicated than we would like it to be. And that pretty much boils down to sine or cosine. But cosine is worse than sine, and the reason why is that cosine is in the denominator. So I'm going to let my u equal cosine, and then my du would be cosine becomes negative sine when you take its derivative. Now I don't see a negative sign in the original problem. That's fine. I'll just stick that negative over on the left, cancel it on the right. And so now my top, sine of theta d theta, will become negative du. So let's make those changes. I've got the integral. Sine of theta d theta becomes negative du. So negative du. And we have 1 over cosine is u. And that has a very simple antiderivative. That's the negative natural log absolute value of u plus c. Now I made up this u, so that's going to become the negative natural log of cosine theta plus c. And that's a good final answer right there. If you open up a textbook, though, that may not be the answer that you see. You might see that it actually says the negative natural log of secant of theta without the negative. And you might be wondering, well, where the heck does that come from? So we can actually do a little bit better than this. We can rewrite this as the natural log, absolute value. And that negative on the outside, remember that that can come inside of a natural log as a power. And we're using -1 as a power here, not as the inverse function. So this is not the inverse function cosine. This is the multiplicative inverse of cosine. That's 1 over cosine, better known as secant. So the other, perhaps more common formula is natural log absolute value of secant theta plus c. And that will give us another, perhaps a nicer formula. It has a little less negatives in it, I suppose. All right, so there we have it. Let's do one more example of how we could find these formulas if we were to ever need them. Another formula, let's prove it. Prove that the integral of cosecant x is the negative natural log of cosecant x plus cotangent of x plus c. And now I've wrote that, I'm getting nervous that maybe earlier in the video I forgot to write the plus c. That's the thing that I'll always get on you guys about as well. Never forget your plus c. Okay, but definitely here it is here in my problem. That should be there. Let's make sure that this is correct. And we can do this using substitution. We just have to be super clever about it, all right? So let me show you how you can prove this using substitution. I'm going to rewrite this as cosecant of x. I'm going to multiply this by something that looks kind of random, other than the fact that I see it in the answer. I see cosecant x plus cotangent of x in my answer. And for kicks and giggles, I'm going to multiply it, but I can't just do that, right? But it's all right if I multiply by it and then divide by it at the same time. That's certainly not a problem. And because that's just, what is this fraction right here? That's just the number 1, and that doesn't change anything about my problem. So why would I ever do this? Well, what I can do now is I can distribute the cosecant across the numerator, and that results in cosecant of x squared plus cosecant x cotangent x all divided by cosecant x plus cotangent. So what on earth do I need to do here? Well, I've got this awful denominator that's confusing me. I would rather just let u equal that. And what you might notice is that, well, hey, what is the derivative? It's exactly, well, almost exactly the numerator, right? Du would be negative cosecant, would become cosecant cotangent, and cotangent would become negative cosecant squared. So that's not quite what we have in the numerator, but again, we'll just do what we did last time. We'll stick a negative on the left, make the right side positive, and this is all, you can assume this is all in parentheses. That's exactly the top of my fraction. So putting this all together, what do I have? This is simply the integral of 1 over u du yet again. Sorry, what did I forget? I forgot the negative right here. So negative 1 over u du. And that results in negative natural log absolute value of u plus c. And that gives me negative natural log absolute value. My u is equal to cosecant x plus cotangent x plus c. And that finishes the proof right there.